Okay, so in the last recording, basically as soon as we left our outbreak rooms, my Zoom crashed. And so we had to restart the call and basically kind of couldn't do normal presentations. Um, but we ended up getting together and we talked about our problems and asked questions and that kind of stuff. But we still haven't gotten a chance to go over the key. And so this is a separate video that will go over the key and kind of just a guide of how do you get work through these challenge problems. And so this first one, really you're just going to want to notice that you've got a um, two different sites where you could have an electrophile or a nucleophile, sorry. And I actually denoted that with yellow, which is why I kind of screwed up in my head. But you'll notice that this one's actually fully covered up with the alkynes, or yeah, alkanes. And so it's actually too covered up to be a nucleophile. So only this one can. And so then you count out the carbons, 5 carbons. Basically, this one has a mistake. It should be a 5 carbon ring, not a 6 carbon ring. And once you do that, it's important also that you don't use OH, because while OH might be great for like aldol, OH will saponify esters. And so basically what that means is, well, I'll talk about it later, but basically the side chains of esters, the alcohol chains will disappear and be replaced by just hydroxyls. And so also with all of these types of Dieckmann and Claisen, you're going to want to make sure you remember to do an acid at the very, very end. And that's because basically this carbon right here is going to be very prone to, sorry, I got a text, being deprotonated. These are very acidic hydrogens. They aren't going to want to stay around for too long. And actually, when they leave, it creates a huge pi system. And so there's a lot of incentive for the molecule to keep this specific carbon deprotonated. For something to come and attack that, and these electrons to stay here. So you need to use your acid workup. And then also there's a huge energy well there. It's very stable. It's like a low energy state. And when you add the proton, that opens things up to, it increases your energy state. It kind of, by putting on the proton, it locks the reaction. Think of it as you fall in this energy well, but once you have a proton, you have to use something to deprotonate it in order to make it in this reactive form again. And it is more stable, but yet like something very positive. Like for example, like I'll go with a like, I'll just say Br, because this has got a partial positive right here. That's partial. If I can draw the sign. What's that sign again? No. Okay, I'm not going to remember the partial positive sign. There's a partial positive right here. And so basically it's going to come and punch in on right there. And that could be a reaction that could happen if like, you know, you didn't protonate it. So I wanted to talk about that for a second and kind of harp on that. After that, you really just got more of the same. She's using these fully alkylated carbons to prevent you from using these as like nucleophiles. And so it basically says that this has to be an electrophile here. And I'll denote that with this. This has to be an electrophile. And like going to stay on consistency, I'm going to go ahead and go back over the last one and mark the electrophile as well. There's the electrophile. And so you need to create a nucleophile that's going to hit this and create the proper product. After you've done this, you'll need to make sure that you do your acid workup again. For the next part, you've got aldol. We've been doing aldol a lot. Hopefully that's pretty comfortable. You're just gonna use OH. It'll deprotonate this guy right here, this acidic hydrogen. It'll come back and work as a nucleophile on this here electrophile. And then obviously that hydroxyl that's left over is just going to become a leaving group, and so the whole thing will get reduced off. You'll be left with just a double bond on that newly formed bond. Next, we've got aldol again. This time you have to actually draw yourself your own little bad boy. So this first one was cross aldol. This one was just regular. So you're creating an electrophile for yourself. So here's that. The nucleophile has to be here because this guy right here, they put a T-butyl group on the end, which is very stable and not going to be reactive. So yeah, you're going to want to make sure you use the OH and it'll do its business, and that's that. For these, I really strongly recommend categorizing Dieckmann, aldol, and Claisman whenever you see them. Dieckmann is just like involves no extra secondary like reactants, so it's an internal formation of a ring. And then Claisen is the exact same reaction, it's just between two different molecules. And then aldol is similar to Claisen, except for that in the fact that you have the tetrahedral intermediate, and then you've also got the nucleophile and electrophile, that the relationship between those two is very similar in that they have the same functionality in their nucleophile and electrophile, at least to attack, to make that carbon-carbon bond. And then, yeah, that's aldol and Claisen and Dieckmann. Forgot where I was going with that, but hopefully that was helpful. So you'll notice in the synthesis problems, we got one aldol, one Dieckmann, and one Claisen. We can go ahead and recognize that pretty quickly because we go from the formation of a beta keto ester, or no, not a beta keto ester, alpha beta ketone. Is that right? This, you got 1, 2, and an alkene, and then you've got a carbonyl group. Whereas the other one, for Dieckmann, you're going to have the formation of a ring. And then for Claisen down here, we've got one of these probably used to be an ester, and then this guy is definitely still an ester, so beta keto ester. I think that's right. I don't know, man. That's these numbers and names. The names have confused me with beta keto ester. Anyway, so the first question, you should count the carbons and recognize that you've got no new carbons here. You also should recognize that this is just incorporating one new carbon into its pre-existing ring. And then it's probably doing something that's going to like involve osmium tetroxide, ozonolysis, because you're going to break that bond and then probably just reform it in a different way. And so, surprise, surprise, the first step of this is just use ozonolysis. And so, oops, this is really far away. That's just the solvent for ozonolysis. This will be your product. I kind of drew it in a prettier way. In reality, it would just look more like 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. And so it would look like, see on the third one, I'm just set up one. 1, 2, 3 here. 1, 2, 3, 4, 5, 6. I don't think that's right. Here, because then this guy's gonna come out, come back and punch. Yeah, that's right. So that's a better description of what it would really look like for you to recognize. Then you're just, and this one's an aldol, so we can just use OH and be done with her. Done with that bad boy. That's that. The next one's a little bit more complicated because you can see, so I went ahead and like wrote note, you're probably going to need to split this hexane and then make a carboxylic acid into an ester. So you can go ahead and see that you're not adding carbons. There's 6 carbons here, and then there's 5 carbons here plus 1 carbon. So you're not adding carbons across this stuff. So you're definitely just going to have to split this and then make something out of it, and do some funny business with some esters. So to start this, we just have to get a handle on this cyclohexane because it is very stable. Um, we're going to use radical bromination and then eliminate with just ethyl oxide and some heat. Then we're going to use ozonolysis, just as we expected, to make this six-membered kind of straight with an aldehyde on either side. And then from here, you're going to want to make your carboxylic acid. And so to make your carboxylic acid, you're going to need a strong oxidizing agent. I usually recommend chromic acid. And so from here, you're going to need to worry about saponification. And so saponification is when like you have fatty acids or any kind of, I immediately start thinking of biochemistry when I see it, because I think of like fatty acids. So I'm just going to draw like glycerol backbone. Well, tell you what, I'll just draw an ester. And all that glycerol is a bunch of these. And I'm going to go, this is going to be a proper tangent. So I'm going to scroll down to the bottom and get new space. I'm forgetting the exact structure, but basically fatty acids look like this. And then they're just strings. Lots and lots of lipids, just fat, straight alkane segments. And sometimes they'll be a little unsaturated here and there, but generally they just look like that. And so this would be like a glycerol molecule. It's basically like this type of fatty acid over and over and over again. It's called the fatty acid because this is an ester, and if you you can make it, one of these is usually a carboxylic acid. And so when you add just straight OH, as a soap would do, what you're going to do is this is going to come off in the form of an alcohol, and this OH is going to replace it. And that's all saponification really is, at least when it's with a base. You can do it with acids too, but I won't talk about that. I think that's right. That's all there is to it. All that to say, we can't add hydroxyls when we've got esters because they will saponify. And so, yeah, your body uses this for some cool stuff too. I don't think it looks exactly like this though. So where were we? So I say all that to say you're going to need to make your esters first, and then you're going to not be able to use OH. You're going to have to use the basically the basic form of whatever your alcohol is. So for this one, it's methanol or ethanol. If it was methanol, you would need to use just one carbon instead of two. Anyway, from there, you're going to get to this substituent here. And once again, you've got to worry about your nucleophilic carbon being troublesome, trapped in that energy well. So you're going to want to use your acid workup to finish that. I think I might have overcomplicated this by talking about saponification, but yeah, that's all there is to that one. Yeah. This third one is just a matter of recognizing that you got 2 3-carbon bits coming together. And so there's no like new carbons being added. It's just a new carbon-carbon bond, and it's reacting with itself. So the first thing you're going to need to do is create a carboxylic acid. And so hopefully you see, when you see all this stuff, you think of how like you're going to need to use a carboxylic acid. Specifically when you see this ester still here and then this carbon right here and it being right here linked to another like ketone, that this is probably 2 esters that have come together, and one is just one of those leaving groups has just come away. And so in order to form that, you form the esters that are going to be involved in that reaction, you need to start thinking backwards to how am I going to get an ester? And so to make an ester, I need to get a carboxylic acid. To get a carboxylic acid, I'm going to need to start with a primary alcohol. And so you could go backwards from this one and go ahead and say, okay, well, I know that I started with, like I said, this back here, these esters that have come together to form a product here, like this ester. And I know that in order to get that ester, I probably needed to be doing reverse esterification. So I'm probably going to need carboxylic acid. Um, and so in order to get the carboxylic acid out of this reaction right here, or this specific reagent, you're going to need to make sure that you have a primary alcohol. Because if you have a secondary alcohol, you're going to go to a ketone. And so we're going to start out with an anti-Markovnikov addition of a hydroxyl. And then we're going to need to use chromic acid, strong oxidizing agent, to make it into carboxylic acid. And then from there, you've just got to add your acid catalyst and alcohol. And that's a reaction you should know by heart. It's just fissure esterification. So the very first reaction is that. And yeah, that's just regular, not reverse. And from here, you're going to have two esters. And so one of these is going to act as a nucleophile, the other will act as an electrophile. Once again, as always, I've denoted the nucleophile with blue and the electrophile with yellow. Then, once we've done that, we're going to be left with basically this product right here. But this right here is going to be negative until we do the acid workup, which will basically trap that proton there and yeah, prevent you from having any funny business getting added to this carbon right here. That has the really ugly arrow that I just drew. So yeah, that's the final product. Remember not to use OH because it will saponify your esters. And yeah, that's pretty much that. Have a great weekend, guys. Hopefully this was shorter. I definitely rambled some of this, especially about saponification that I didn't need to. But if you're still confused, Google it, email me. I'm available. We'll figure it out. I've got you guys. We're in this together. On that note, I guess I should end this recording.